My name is Yoji Yamato. I'm from NTT Laboratories. Today I'm going to talk about proposal of automatic offloading method in mixed offloading destination environment. This is outline. 1. Introduction. Heterogeneous hardware such as GPU and FPGA increase. For GPU and FPGA control, technical skills of CUDA and OpenShield are needed. In the future, application programmers only need to write logics to be processed, then software will adapt to the environment, I think. Java runs on another machine, but performance is ignored. So I have proposed environment adaptive software to operate on once written application with high performance by automatically converting the code. The purpose of this paper is to automatically offload applications with high performances in mixed offloading destination environments in which various devices of GPU, FPGA, and many core CPU exist. 2. Existing technologies. Java has a problem that it takes much effort for performance tuning and debug on coding destination. It writes once, run anywhere, but debug everywhere. So CUDA for GPU and OpenShield for heterogeneous hardware. There are directive-based specifications like OpenSCC, but performance is difficult even if FPGA or GPU can be used, because automatic parallelization compilers may not improve performances because of memory transfer overhead. And there is research to automate trial and error of parallel processing, but there is a problem that the speed is insufficient. No consideration has been given to proper offloading for mixed migration destinations such as GPU, FPGA, and many core CPU. 2. Proposed environment adaptation flow. This figure shows the adaptation flow of environment adaptive software, which I have already proposed. Step 1 to 6 are done for adaptation before operation start, and during operation reconfiguration is proposed in step 7. First, application is input and analyze application code and extract offloadable area and output intermediate file and measure performances. And this process is recursively done, and after the code is determined, we determine resource sizes, application allocation, and deploy final files to production environment. This paper's objective and contribution. Objective: by automatically performing code conversion and configuration so that the software can be used in the right place on the GPU, FPGA, and many core CPU at the development destination. It can be operated with high performance even in mixed migration environments. Contribution: for preparation, I propose automatic automation for many core CPUs in loop statements using methods similar to GPU case. And I propose an appropriate order of offloading verification for a single migration destination in mixed migration destination environment. I propose a method of offloading to multiple devices when it is possible to offload to multiple devices on one node. I evaluate the effectiveness of the method with existing applications. 3. Basic idea. There are 3 operating devices: GPU, FPGA, and many core CPU. From the history of offload use and market size, I choose these 3 devices. In order to automatically offload, the performance is measured in the verification environment, and the high-speed offload pattern is gradually found by combining with evolutionary computation method. As for performance, it is difficult to predict statically because it varies greatly depending not only on the code structure but also on the specification of the hardware, data size, and other processing contents. The offloading targets are loop statements and function blocks. Since most of the processing that takes a long time to process is spent in the loop, so the loop statement is considered as a target first. When speeding up a specific process, the function block may greatly improve by using an algorithm suitable for the processing content and hardware. 3. 2. Preparation. Automatic loop offloading many core CPU. Firstly, I prepare automatic loop offloading of many core CPU. Approach. To confirm the speed up by the GPU offloading equivalent method. Many core requires OpenMP to utilize its core computation power, and conventional manual operation is large. So, propose automatic offloading loop statements to many core CPU. It specifies parallelization with the OpenMP directive pragma OMP parallel for the loop statement, and to extract the appropriate loop statement by the evolutionary computation. Unlike OpenSC, OpenMP generates wrong results when pragma specifications are wrong. Therefore, the fitness of the pattern is set to 0 so that it doesn't remain by checking answers. So these are code patterns, and for each for loop statement, it specifies pragma will be parallel or not. And for each offloading pattern, we measure performance on verification environment and select high performance code patterns, and generate next generation code patterns by genetic algorithm. By these methods, these 4 applications improve performances more than 4 times. We use a licensed Reaper for many core CPU. 3. 2. Automatic offloading to each offloading device. Since there are offloads for the migration destination environment, GPU, FPGA, and many core CPU with loop statements and function blocks, so there are total of 6 offload patterns. As a verification order, I propose offload of many core CPU function block, GPU function blocks, FPGA function blocks, many core CPU loops statements, GPU loops statements, and FPGA loops statements. These are orders, function blocks, then a loop offload check. Function blocks are likely to be faster, and FPGAs will be left because it is desirable to find solutions as quickly and inexpensively as possible. 3. Automatic offloading for mixed offload destination environments. If one node with multiple devices, it verifies if it is faster than a single one. For example, one node has a GPU and many core CPU. If different function blocks can be offloaded to different devices, then it targets those function blocks if they can be offloaded to the same node. If different loop statements can be offloaded to different devices and can be offloaded to the same node, the loop statement with higher performance are offloaded fast. Then the remaining loop statement are offloaded to devices where the performance improvement effect is low. 4. Implementation. Proposed method is implemented using following tools. Implementation tool Perl and Python. And GPU, I use NVIDIA GeForce. And for GPU control, PGA control compiler is used. For FPGA, Intel PAC with Intel Arria 10 GX FPGA is used, and I use for FPGA control Intel Acceleration Stack version 1.2. For many core CPU, I use AMD Ryzen 3 Reaper, and for many core CPU control, I use GCC 10.1. For parsing tool, clone is used, and similarity detection tool, I use Record. And for code pattern DB, MySQL is used. And arithmetic intensity analysis, I use Rose framework. And difference check for CPU results, pcast function of PGA compiler is used. And this is outline of implementation. It carries out offload trials in 6 ways. The function blocks are the same for many core CPU, GPUs, and FPGAs. For loop statements, on many core CPU and GPUs, loop optimization charges performance on GA. And load is used to narrow down to loops with high load and try for FGA. If there are prior methods that can be accelerated in 6 trials, and if they can be offloaded to different devices on the same node, it tries a combination. Evaluation condition. I evaluate applications of matrix calculation, block triple diagonal solver, signal processing, and the combinations. For condition, loop number, Polypens 3mm has 18 loops, NAS PT has 120 loops, TDFIR has 6 loops. And for function block detection methods, similarity detection decode is used. And loop genetic algorithm, these are genetic algorithm condition. And parameters of performance measurement, these are parameters of performance measurement of 3 applications. This figure shows environment condition, evaluation environment. I use Ryzen 3 for mini core CPU and NVIDIA GeForce for GPU and Intel PAC with Intel Aria 10GX FPGA for FPGA. Uh, Results for all three applications. The method selects the faster method and offloads. For 3mm, 3mm's 1000 and 1120 times with GPU loop offloading, and for 4.5 times with many core CPU. And NAS bit is 5.39 times with many core loop floating, and GPU doesn't improve. TDFIR is 21 times for FPGA function block offloading and 4 times for FPGA loop offloading. Results 2. In case of multiple devices with one node, using appropriate device makes it faster than offloading to a single device. With both 3mm and NAS-PT processing in one application, total performance is 6.58 times. For when we use GPU and many core CPU for 3mm and NAS-PT processing, total performance improvement is 6.58, but when we use many core CPU only or GPU only, performance improvement is less than 6.58. Conclusion. I have proposed environment adaptive software for adapting application to the environment appropriately utilizing GPU, FPGA, and so on. I propose an offloading method to mixed destination environment. As a preliminary preparation, I propose an evolutionary computation method similar to GPKs for many core CPU. What of offloading attempts on a single migration device destination? Main core CPU function block, GPU function block, FPGA function block, main core CPU loop statement, CPU loop statement, FPGA loop statement. And offloading when multiple devices on the same node are available. The method offloads to multiple devices to verify overall performance and compare with single device offloading. I implemented proposed method and verified whether the offloading to mixed destination environment is effective for existing applications. In the future, I will consider a common offloading method that can handle not only C language but also various languages such as Python and Java.